Hello everyone. My name is Berat Aydın, and I'm with my teammates Atif on my left and Taylan on my right. We want to present you our project higher order SVD and video compression. We did this project for the course EEE-587 for the spring 2022 semester, given by Stefano Rini. We want to do a project about video compression, and we abandoned our previous idea because we thought that the video compression research on video compression was very much motivated by the real life facts. Let me share some of them with you. I will show you some data that I can easily find on the internet. Like we can see that only Netflix is responsible of the 15% of the total internet traffic nowadays, and we can see that most like other video applications also take a lot of the current internet traffic. And like there's this another data which shows that around 70% of the internet traffic during the evening hours is just streaming video and audio data. So we can say that improvements on the video compression algorithms, like relating to bitrate or relating to quality, would be very beneficial when the scale of the industry is considered. And during the semester in our course, we have seen methods such as singular value decomposition, random projections, or row and column sampling. Such random algorithms allow us to gain computational advantage when we are willing to sacrifice some accuracy. And in our case, we wanted to see how these can be applied to video compression purposes. We can say that a video is most intuitively can be represented as a tensor, because a video consists of images, and each image consists of pixels on 2 dimensions. And a video also has the temporal dimension, and also it includes 3 different color channels. So in short, a video can be represented as a 4-dimensional tensor, such as this one, for example, depending on the resolution. Let's say such a data can represent a video of 60 frames with this resolution with 3 color channels. At this point, we should consider how the randomization methods can we apply to such a tensor to achieve compression. And okay, at this point, let us consider tensors more formally, mathematics-wise. A tensor is a mathematical object consisting of real numbers with any specified dimension. As you can see, of course, it has to be finite. And for our project, we specifically considered Tagger decomposition. This is a decomposition that exists for any given tensor. And let me state it. Given a tensor T, a Tagger decomposition of it exists such that, considering this multiplication operation, and I will explain this multiplication operation later, and the decomposition products are another tensor S, which has the same dimensions as T, and these Qn matrices, each of which has this specified dimension you can see here. This decomposition exists for any given tensor, and this specific multiplication operation that we see here is defined in this manner. And as our main idea is randomization, low rank approximation, and compression, we we can say that this Tucker decomposition can be approximated by using a tensor as of lesser rank than it is supposed to be. For example, we can specify these ranks R1, R2, Rn instead of the previous I1, I2, In. And in that case, these Qn matrices will have the size Rn times In instead In times In. And in this manner, we can see that the number of, let's say, double data that we have to store on the right-hand side is given by the numerator in this fraction. And the actual data, which is the tensor T, has this amount of, let's say, double data points. This means when the R values are selected carefully, this can give us a very good compression rate. In this manner, compressing means that extracting this as tensor and Q matrices. This will have a smaller size when R values are chosen appropriately. And in this framework, decompression means performing this multiplication to get an approximate T tensor. In order to calculate the deterministic Tucker decomposition, we have to calculate what is known as a folding matrix of the tensor. A folding matrix of the tensor has such a size as you can see here, and there are n different folding matrices for a tensor with size n. And after each of these folding matrices are acquired, then a full SVD is performed on them, and the U matrix for these SVDs are later used to form the Qn matrices in the deterministic Tucker decomposition. But in the randomized case, we will not follow this line of argument, and we will use some specific randomization to decrease these Q matrices and the S tensor in size. At this point, my friend Thailand will continue to explain more about the specifics of the algorithms that we have used.
Hi everyone, I'm Thailand, and I will show the algorithms we have implemented in our paper. Not the paper, the project, of course.
No problem.
Okay, we have studied a paper about higher order SVDs, but we didn't implement all of them because there were like 9 algorithms involved in the testing, their testing. One of the algorithms we studied was based on column sampling of the matrices, the folding matrices. One is based on random projection, and the last one randomized SVD, which is also based on random projection with SVDs, of course. So the first algorithm here is the random projection higher order SVD algorithm. We have a data tensor, as Berat talked about, with n dimensions and a multilinear rank, which is the dimension reduction, the dimension we want to reduce to. And we output the approximate higher order SVD, the Tucker decomposition here. First, we form an auxiliary matrix as Z, auxiliary tensor. For every dimension of the tensor, we compute this random projection, which involves the omega matrix, which is formed from Gaussian entries with this dimension. And then we take the QR decomposition of Wn, and we form the projection matrices with this, the QR decomposition. The Q matrices will come from QR decomposition in this case, And then we compute the core tensor as follows, as we showed before here. We construct the approximate tensor. So this algorithm involves the random Gaussian projection, which reduces the dimension to R1 to Rn. We have a 4-dimension case, so n is 4. And the QR decomposition here reduces the runtime to respectable levels here. The second algorithm is randomized sequentially truncated higher order SVD algorithm. We have the same inputs and outputs, the data tensor and the Tucker decomposition, respectively. We start by forming the core tensor S from the folding matrices of X, firstly. Then we apply another specified algorithm in the paper to this n unfolding matrix with target rank Rn, the nth entry on the multilinear rank array. Then we start forming the core tensor, the reduced dimension core tensor here. Let me show you algorithm 1 here, which is about randomized SVD. The algorithm they used here is data matrix and the random projection matrix with an oversampling parameter. We start by forming this power iteration matrix with a Q power iteration parameter as a power iteration parameter. We compute the QR decomposition of Y and then compute the project matrix on X and the SVD of B. And we apply the following. This is used to form the factor matrices of the Tucker decomposition. The last algorithm we tried is our randomized sampling Tucker approximation, which is directly sampling, which is based on directly sampling the matrices in order to approximate Tucker decomposition. Okay, we sample some columns of the nth folding matrix of X, and then store them directly in the factor matrices. Here, this is a much more basic algorithm, and we compute the core tensor by taking pseudo inverses of the factor matrices and the data matrix. Overall, those 3 algorithms we will try in our simulations, and the simulation setup is what I will talk about next. We talked about our algorithms, so for the computation, we had a computer with 16 gigabytes of RAM and 8 cores, as opposed to the Alter's 500 gigabytes of RAM and 48 cores. So this caused bottlenecks in our system. We also wanted to compare our results with the state-of-the-art codecs such as AB1, VVC, and HEVC, with the compression rates and the video quality metrics, and on a known video dataset. But because we had such a computational bottleneck in our system, we couldn't do any of these fully. Also, the video codecs I just talked about have a lot more going on than just compressing and decompressing, like filtering operations to make the video more realistic. We did not implement those steps because it will not be a fair comparison with the paper or another compression algorithm. So for example, for our videos, we had 1920 by 1080 RGB videos. The size of a 10-second RGB video, 1080p RGB video, played at 60 frames per second for 10 seconds would occupy 29 gigabytes in memory if every element is stored as a double 8 bytes. This is the reason we could not work with the full data. We only took the first 60 frames of the videos in our system.
Okay, so
So my friend Atif will talk about the results and the discussions.
thank you, Daya. So I will talk about the video quality metrics that we wanted and we computed for our algorithm. So first of all, we noticed that the Frobenius norm is not a very good measure of the quality, especially when we talk about images or videos. So there are some specific metrics like PSNR, SSIM, and VMAF that are of objective, that measure the objective quality of images, and VMAF is specifically designed for the videos. So yeah, video quality is a is a characteristic of a video, like where we compare a like distorted or a compressed video with the original video, and we measure like the artifacts. And to measure it, we have some some mathematical objective quality metrics. Those are like PSNR, SSIM, and VMAF, as I talked earlier. So like if we talk about the PSNR, it's a peak signal to noise ratio, and it is usually computed for images. So for our data set, we did it image by image and just computed the mean for all of the frames. So if we talk about a grayscale image, so this is how it's computed. So you compute the MSC of a full grayscale image, and then you calculate this PSNR as in a dB scale, where the max I, it is the maximum possible pixel value of the image. So for an 8-bit case, it is a 255. And our videos, like we have 10-bit videos. And for the RGB videos, this is similar, but we sum it over all 3 channels. The second quality metric that we used is SSIM, that is structural similarity. It is more widely used than PSNR, and it's a better measure. So this we also calculated this frame by frame, and this is represented by this Q, the equation given here. So the 3 terms, as you can see in this equation, are for the loss of the correlation, luminous distortion, and contrast distortion. So there is also a new metric, that's VMAF, Video Multi-Method Assessment Fusion. It is based on a neural network like SVM. It's an SVM-based regression to provide a score between 0 and 100. That is the quality of the video when we compare it to a regular video. So it is developed by Netflix, and it is one of the state-of-the-art video metric. We wanted to compute, we computed PSNR and SSIM for our algorithms, but we couldn't compute VMAF because setting it up and installing it was a hassle, and that we couldn't do like in this short time. So like if we come to our results, so here you can see our results for 3 different algorithms that we are saying algorithm 6, 8, and 10 from the original paper referenced in citation 1. So this is the first metric that we report. This is the SSIM, that is the similarity index. And we have plotted it against the compression ratio. Like on the x-axis, if we move from left to right, like it means that we are compressing the video less. So we can see this from the blue curve algorithm 8, that as we compress the video less, that we allow our multilinear rank to be more. So our SSIM increases from 0.85 to up to 0.98 or something for algorithm 8. For algorithm 6 and algorithm 10, like as we didn't do a lot of simulations and took the average, these results are just from a single run.
So like there is some problem here with this curve, but this algorithm works as it should according to the intuition. And on the right, we can see this PSNR. This is the peak signal to noise ratio. So this is also a metric for image compression. So for algorithm 8, like it starts from 20 and goes up to about 30 as the compression ratio is increases, or we can say that we compress the image less. So this compression ratio is defined as the size of the compressed image divided by the size of the original video. The size. And now, like here, I will show you the running time of these three algorithms. So the algorithm 8 like performs the best, but it also has the worst running time. So it takes about 300 to 400 seconds to process our fourth order tensor that has 60 frames. That's about 1 second of video. And then algorithm 6 and then algorithm 10. Algorithm 10 is the fastest. And on the right, you can see the rank that we use to compress the video versus the compression ratio. So as we increase the rank, you can see that our compression ratio metric, this is increasing. So it means that we are compressing the video less. So this last plot is, we also plotted the Frobenius norm. That is the normalized Frobenius norm MSE versus our compression ratio. And for algorithm 8, we can see this, like the Frobenius norm increases to a very low number as we compress the videos less. But for other two algorithms, it is very oscillatory. It can be due to because we don't have a lot of simulations, and this is a random experiment. And for algorithm 6, like there might be a problem in the plot, I guess, here, because otherwise this algorithm also behaves good and this error should come down. Also, like let me show you a video like that we compressed using these three algorithms. Okay, so for the conclusion, so what we have achieved in this project, we have explored the possibilities of the video compression using higher order singular value decomposition. And we have also seen that Frobenius norm is not always a good error metric, especially for images and video data sets. And we implemented 3 different randomized HOSVD algorithms for video tensors and reported our results. And with this time and computational constraints, we tried to explore this field as much as possible, but we couldn't achieve everything that we wanted. Thank you so much.
Thank you.